Good day, welcome back. I'm sure you are enjoying learning all the sessions previously and you are more comfortable in using different peripherals and how the bus connections are happening and where you are using and also the related registers. If not, please go back and revise. We are on day 23. Today we're going to learn about I2C. I2C as such is a long and big concept and module as such. So I don't want to put a lot of information in one part. So I just classify into 3 different days dedicated to this. The first day will be about just the initialization of it. And then there is part 2 and a demo session. Today's session you will learn about what is an I2C and where it is used and how we're going to integrate that in your program. And also you're going to learn the basic difference of the I2C and the SPI. So both are communication protocols and you will learn about the differences. But we have a dedicated session for SPI where I'm going to talk to you in detail about the SPI. Today you also will learn to code line by line for an I2C on the initialization part. Before going there, I would like to introduce myself. I am representing I2DG. It's a startup by Anbukarasu brothers, my brother Alex and myself in Arul in 2023. Both of us gathered over 20 plus years industry experience, and we would really like to put it out there for you all so that it would also help you to be a better professional. And our mission is to convey our knowledge and our experience to at least 100,000 future professionals through our online courses. And the main advantage is you can study anywhere at any time, wherever you are. So that's really good about that. A little bit about me. I'm Arul P. Anbukarasu. You can call me as Arul or API, as persistent as I would like to be to share my knowledge and experience with you all. I have 20 plus years experience working in various industries in Australia, Italy, Singapore and India, majoring in renewable energy sector, that's in solar and wind conversion, power systems in lead acid batteries, network embedded systems, it's connected with ATMs, TCRs and point of sale machines, banking automation systems and smart parking operations. And my expertise lies within these 3, the embedded systems, VLSI and project management. A small announcement to make. I categorized into 2 different categories. The first is the YouTube viewers. All the videos should be uploaded to I2DG YouTube platform, so please to go and check all the videos. In order to be eligible to get a free certificate, you got to attend at least 28 video sessions. And at the end of session, you will have an attendance link, so you need to fill that out and send it across to us, and that will automatically give you allocation to give you a free certificate. And part of the YouTube regulations, the videos can't live there longer, so it has to be removed after 2 or 3 days. So therefore, if you miss one day, you may not be able to go back and revise. So that is a drawback. That's why I strongly advise you and recommend you to join one of our internship programs, because this will give you not only the internship certificate, but also you will get the online session to yourself. So you'll have a separate login, so you can log in and go through day by day session. And this internship certificate will count a lot towards your career in when you land for that interview or when you got the job and when you start to work with your senior engineers. They consider this 30 days journey is a lot, because you go through the tough period, you learn everything from scratch and you can build things from scratch, and you know what is involved in terms of embedded system design, and you can do your own design by then. So please do invest on this, and you won't regret it, but you will earn a lot from this. Not only that, you will get unlimited access to all our course contents, all the PDF materials, the source codes, the reference manual, data sheets and everything, whatever you need. And also the unlimited account with your course videos, so you can go back and listen to it, and if you want you can pause and go and do something else and come back to it, and if you want to go 3 days further back, you can also do so, because it's all yours to keep and you can do with that. And in case if you get stuck with those things, please contact with our backend support team, and they are a friendly, lovely team, and they will be able to help you move along in your learning curve. So shall we getting to communicate and see what is our first or second, I should say, second communication protocol, because we already learned USAT. This is our second. So let's get in and learn about I2C. What is I2C? As you know, most of you, because you gone through your engineering days, you might have heard this term or this icon many times, and you would also know its abbreviation. I'm just giving a recap of that. Sorry to be a repeat. I2C is abbreviated for integrated circuit, and generally it is called as an I2C or I2C, and also the other names in the industry you would hear it's a two-wire interface or TWI. What's happening with your TWI program? Can I use that in my main program? Sort of hearing that you will hear from your senior engineers in the industry. So these are all some terms there. So I'm letting you to experience that. So where I2C is used, I2C can be used to interface with different sensors, and also it can be interfaced with the memories. So that's where mainly the I2C is used. I2C is used for one of the communication protocol between a microcontroller to another microcontroller as well. You can do that. And also in various different areas of communication, I2C comes in real handy. And I2C requires only two lines. Yeah, you need only two lines to communicate your data through that. Those two lines are serial clock and SDI. The serial clock is used for synchronizing the data transfers between the master and the slaves. In I2C, the main advantage is you can have multiple masters and multiple slaves, but the distance coverage is a bit shorter compared to the SPI. And the serial data, that's the data line. That's where you send the data to master to slave. And this is how the communication is done in these two lines. And the communication can be done in 4 different operation modes: the master transmitter mode, master receiver mode, slave transmitter mode, and slave receiver mode. You will get to learn after you know the basics of today. You can also use in different modes. So today will be just the brief about all the modes of it. And these are all the different bus terminologies that's related to I2C. Start with transmitter. You already know from USAT what a transmitter and a receiver is. A transmitter is the one which you can use to send data to the bus, and the receiver is the one you can receive data from the bus. And today you're learning a new concept about master and slave through I2C. Master is the one which can initiate a transfer of data. It can generate clock signals by its own, and it can also initiate a transfer, and also it can terminate a transfer. Being a master, as you know, master is all, so it can control everything. And the slave, this will be addressed by the master, so the master has to contact the slave. So that's where slave is used. And also there is a multi-master. You can have more than one master in your application. And there is a new term called arbitration. What is this? Arbitration is nothing but if you have multi-masters in your communication protocol, if the second master device want to start to do the transfer of data, then it can't do so. But if you have the arbitration in that, what it does is the second master will be waiting for the first master to complete its register transaction, and then the second will start and it will start to transfer. So that's what basically arbitration is. Arbitration is a procedure to ensure that if more than one master simultaneously tries to control the bus, but only one is allowed to do so, and the winning message is not corrupted. So whatever the message has to reach to the slave shouldn't be corrupted. So that's why the traffic between the data channels. So that's where arbitration is. Synchronization is nothing but the procedure to synchronize all the system clock signals and then deliver the clocks to one or more devices. So these are some of the terminologies. Then we see the protocol. The protocol is the transactions of the data transfers are initiated and completed by the master. So the slave will act whatever master asks it to do, the slave device will work. And all the protocol, the messages will be sent in this format as an address frame and a data frame. So every I2C device will have its address frame and also a data frame, which you will see in the next slides. Data is always placed in the SDA line, and when the data transfer happens, first the SCL will go low and it will be sampled, and after this line goes high, then the data will start to transfer, which you will see in the next slide. So the protocol works in the I2C with a start and a stop condition, and the first one is the I2C start. I2C start is when the serial data is, when it transitions from high to low, the serial clock also will follow that, and it will go from high to low, and this is a start condition. And the stop condition is the other way. The SDA will go from low to high, and also the SCL will follow the data line, and this will also go from low to high. So high to low is a start and low to high is a stop condition. That's the basic difference. So this is how in I2C a message is transformed or transferred from master to slave. First it will start with the start bit, the SDA line and the SCL line. Once the SDA line and the SCL line goes down, then it will send a address package to the slave. So the slave address will have, mostly it will be a 7-bit or 10 bits. In this example we are using 7 bits, and then there will be a bit after the slave address to decide whether that's you're going to read from the I2C or you're going to write it. If it is 1, if this bit is 1, you will see in the next next slide, then it is read. 0 means write, and as soon as it gets the slave address from the master, the slave will send an acknowledgement to denote that yes, I received the slave address, so now I'm waiting for the data. So then the data will be sent as in 8-bit format. So first the MSB will be transferred and the LSB, and then once the data is delivered, then you'll get another acknowledgement from the slave, and then you get, once the data is completed, then you'll get a stop bit. That means you conveyed that particular message frame being transported from master to slave. And these are all the explanation that you can read yourselves. When you read through, then you'll understand. Just adding to that, each byte must be followed by an acknowledgement bit, so the data is transferred to the most significant bit first. So that's what this. The address frame is first, so this is the address frame in any form of new communication. So when you do a read, then the read write should be 1, and when it is, you set this as 0, then that means it's a write operation. And this is the protocol with the data frame. The data frame begins transmission after the address frame is sent. So as I said earlier, it has to wait for the I2C address to be first recognized and send the acknowledgement, and then the data will start, and then followed by another acknowledgement, and then the data will be sent in n bytes. So it depends, mostly it will be sent as 8 bits. And when we talk about the I2C clock speed, there are 4 different modes. This is the speed of the I2C interface, how it interfaces, how fast it can process. And it should correspond with the corresponding bus speeds as well, that is defined in the I2C specification. According to STM32F411, the standard mode is 100 kHz, so that's what we're going to program with. And the 4 different modes are, if you want to set that to 400 kHz, that's the fast mode, and the fast mode plus is 1 MHz if you set the clock speed, and the high speed mode is 3.4 MHz. So these are some other clock speeds. And then you need to determine the I2C duty cycle. It defines with the ratio of the timer low with the timer high on the SCL line. So the possible values for the duty cycle is 2:1 or 16:9. By choosing the appropriate duty cycle, you can also pre-scale the reduction of the speed, so to control when it comes to the peripheral clock to achieve the desired I2C speed. And now we're going to see the differences between the I2C and SPI. As I2C comes in two different forms in the output type. One is push-pull and open drain. In this example, we're going to learn about the open drain because in order to make the NMOS resistor, transistor to work, you need a pull-up resistor to lift it to make it connected. So that's why a pull-up resistor needed. What is the difference between the I2C and SPI? As I said, SPI will have a different session to it. Today we are just knowing the basic difference. I2C has half duplex communication. What is half duplex communication? It simply means at any one time you can only either transmit or receive. You can't do both together, the data packets. Whereas in SPI it is a full duplex communication. That means at any one time you can also transmit data and also receive data from the ports. And I2C supports, as we know, supports multi-master, multi-slave arrangements, whereas the SPI doesn't. I2C, as you know now, it requires only two lines, the serial clock and serial data, but SPI works on a 4-wire protocol, which you will learn. I2C supports clock stretching. Clock stretching is if you have multiple slave devices, then the particular clock, the system clock, can be looped and linked, connected to the number of slave devices that you want to connect. So that's what clock stretching is, that it can be stretched to connect all the slave devices. Whereas the SPI doesn't have that clock stretching. Instead it has a chip select, so therefore it needs extra wire for that. So that's why it little bit different settings to I2C. Comparatively with the speed, I2C is slower than SPI. The maximum speed is the peripheral clock divided by 2, so that's comparatively slower compared to SPI. In STM microcontrollers, I should say, maximum speed is just about 400 kilohertz. When the data rate sent to receiver in 1 second, that means it calculates everything and compares with 1 second data transfer rate. So that's how the speed is determined from I2C and SPI. So comparatively, I2C is slower compared to SPI. I2C has extra overhead start and stop bits because it doesn't have a dedicated line to use, so it only communicates through a start and stop bits, whereas the SPI doesn't have it. It has a chip select bit, so which is different, which you will learn. And I2C has the luxury of sending an acknowledgement back after every byte is transferred. Then it lets the master know that that pack has been received and sent, which SPI doesn't. So that's really a good difference. So these are all the basic differences. Now there is a certain procedure steps you got to follow when you want to access your slave from the master using I2C. So this is how you do it. Suppose a master wants to send data to a slave. How do you do it? The master transmitter mode, as you know, there is 4 different modes that you learned. We're going to use the master transmitter mode for that. The master transmitter always sends a start condition. You know the start condition. The SDA line and the SCL line will be transitioning from high state to low state. That's where the start condition occurs. And then it sends the addresses to the slave receiver. That's the second, another mode of the 4 operation modes. It sends to the address to the slave receiver. And then the master transmitter, once it sends the addresses, then it has to send the data to the slave receiver. And then it terminates after it gets the acknowledgement from the slave receiver. After that 8-bit of data frame transfer across, it will get a acknowledgement. And then the master transmitter mode will know that you need to stop it and then start the process again, send the next set of data. So that's how a master will send data to a slave. If a master wants to receive or read from a slave, we just seen how a data can be sent to a slave. But if you want to read or receive, this is the steps it has to consider. And please remember, every time when a master starts, it will always have a start and it will finish with a stop. So those two are really the main must. So with the other options of receiving or reading a data from a slave, then it works in this mode, master receiver mode. In this master receiver sends a start condition and addresses to the slave transmitter, because the transmitter has to acknowledge and send its data back to master to read or receive. So it's the other way around. To send a data, it's a master transmitter to slave receiver. To read a data, it is from slave transmitter to a master receiver. So that's the basic difference out of it. Then the master receiver sends the requested register to read the slave register. So the master will send an address, okay, I want to read from this particular location, and it will also send a register of that particular location to the slave transmitter. And the master receiver receives the data, because the slave transmitter knows which to send. So it will send that data back to the master receiver. And once the master receiver receives the data, then it will send a stop condition to stop, and the process will goes. So this is how the two differences about to send a data and receive a data. And also we're going to see about the I2C protocol timing diagram, how the address frames and data frames are structured. This is the SDA and SCL line with the address frame and data frame. So the first is the start condition. As we know, the SDA and SCL, it has to start from on to off or high to low position. That means it's a start condition from the master side. And then it sends the address frame after that, 7 bits of address frame, makes the I2C address for that particular data message. And then you get this read or write bit. If you set that to 1, that means master wants to read from the slave. If you set that to 0, that means the master wants to write to the slave device. So that's that bit. And then you get the SDI acknowledgement bit. After every time when a packet is transferred, you get the acknowledgement. Once you receive the acknowledgement in the next cycle, then you are allowed to send the data to the slave. So you will send that in an 8-bit frame. So that's the D7 to D0. Then after it receives the data signal, the data, then it will give the condition acknowledgement saying I received the data. So then the master would know to send the stop bit. So the stop bit is where the low transition to the high transition, that's what classified as the stop bit. So this one particular whole from start condition to stop condition, it's one frame, one message transfer. And one message transfer is performed by an address frame and a data frame. Starts with the start condition and ends with the stop condition. After every address frame sent, the acknowledgement is received, and also before the acknowledgement receiving, then it has to determine whether it's a read message or a writing message, and then accordingly the data is sent or received accordingly. So that's how it works in I2C. And this is to explain in detail about the bits. This is to write to a slave, writing to a slave on the I2C bus. First it starts with the start bit, then the slave address of 7 bits will be transferred. Then to write, as we'll just learn, we have to set this bit to 0, and after that it acknowledges saying I received the slave address. Then it has to send for every data, as you know, because this is where the data is saved on these registers. So all the data registers will be sent first, and then the acknowledge. After that the registers acknowledge, then the data frames will be sent. Then once the data is sent, then you get the acknowledgement bit. Then the master would know, okay, now is the time to send the stop. It will send this stop bit. Whereas reading from the slave, so first you got to write, and then you need to do the read. So continuing with the last bit example, first the start bit starts and then sends the slave address. It's still writing, so the first data is written, and the register for this particular register, so it's asking to be read from this slave address. So it's sending these registers, and then the next repeated start again. So every time when you want the slave address to be accessed, it should have a start. So this time it knows that it has to be read from the slave to the master, then you got to set this read write bit to 1. That means it's reading the particular register, and then you pass the data frame for that from the slave address to the slave register, and so forth. You will get to read. So this is the difference in the packages. And this is the example in the STM32F learn. As I said, it works in the output type works in push pull or open drain. We're going to program with the open drain, and we need pull up resistor. We learned a lot in details in previous sessions, so please refer to that and you will have better understanding of this output type. And this is the functional block diagram in the data sheet. If you go to page 15, this is what you will see, and that's the expanded version of this I2C bus. So we have this I2C peripherals, I2C1, I2C2, I2C3. In our example, we're going to learn I2C1. So I2C1 is connected to advanced peripheral 1 bus, so you need to enable the clock, and also this through this bus it's connected to the bridge, and the bridge connects to the advanced high peripheral bus to the matrix, and the matrix connects to the microcontroller. So you got to enable the high performance bus clock and the peripheral clock for a start. Slowly at the demo side, that's the third session from now, you will be integrated and interfacing with ADXL345, that's the accelerometer, and you're going to use these two lines in the small PCB, which is connected to SDI and SCL. So PB8 will be connected to SCL, PB9 that's port GPIO port we're going to use, and you're going to connect to the I2C1 on the STM32. So you need to connect accordingly. Check for the port pins and you're going to interface with that. These are all the steps you need to consider for writing the initialization code for I2C. First, you need to say which mode you're going to configure, either standard or fast. Then you need to set what speed that serial clock has to run. So you need to set the speed of the serial clock. Then configure the device address applicable when the device you're going to use is going to be a slave. Then enable the acknowledging, whether it's a slave address or a data frame send, so you need to enable that. Then configure the rise time for I2C chips. You need to also set the rise time. All these has to be done when the peripheral enable mode is disabled. That means PE is 0. So these are all the must you need to follow. Continuing further, you need to set these two control registers to use the peripherals. In STM32F411, the I2C peripheral, to use the serial clock control settings, you need to use the control register 2 and the control clock register, CCR register, to control the I2C serial clock. So you got to set these registers to use the CR2. And this is a CCR. You need to set bit 15 as 0. That means you're using for I2C, which you will learn in the program. And to control the clock control register, you got to, this is how you calculate. So as we see in the basic functional diagram in one of the pre-scaling example I shown, it comes with the high-speed internal, high-speed external clock and the phase lock loop. All the clocks are sent to the mux, and we need a system clock, and we were using only 16 megahertz for this, and that's been fed to the APB1 because that's the one that's connected to I2C1. So the APB1 bus connects the maximum of 42 megahertz, but that's why we're using the pre-scaler to get 16 megahertz out. So 42 will be divided to get the 16 megahertz, and the 16 megahertz will send to the I2C1 as a CCR setting. So in the next slide you will see a small example how the CCR calculation is made, and this is how the serial clock is sent to the application to transfer. This is the example. In the standard mode, to generate a 100 kilohertz serial clock frequency, the peripheral clock will come with a 16 megahertz. So first you need to configure the mode in the CCR register 15th bit to say that you're going to use it as an I2C bit. Then program frequency field of CR to the value of peripheral clock 1. Then calculate and program the CCR value in the CCR field of the CCR register. So this is one example. To transfer the duration of 10 microseconds for the on time and the off time, this is how the formula is: 5 times 10 power minus 6 equals the capture control register times the 62.5 times 10 power minus 9. So to calculate CCR, then you need to get this value, and you will calculate and get it as 80 as a decimal, and in hex you can write it as 0 cross 50. So this is what you need to feed in as a CCR, the clock control register rate. So these are all the steps we will be seeing in the program, and you're going to first enable the clock access to port B that's connected to the peripheral bus to I2C1. So you need to enable both port B because you're going to use PB8 and PB9, and the I2C is connected to APB1. So you need to enable both the clocks. Then set PB8 and PB9 to alternate function as output, and then set output type as open drain. As you know, there is another one called push pull, but we learning about open drain. Then set the internal pull up for both open drain for the both PB8 and PB9. Then set the alternate function type for I2C. You need to set that I2C bit as alternate function as you're going to use it for the output. Then it has to enter to the reset mode and then out of the reset mode. So these are all the steps. And then you need to set the peripheral clock frequency to 16 megahertz, and then set to the standard mode as I2C 100 kilohertz. So there you go. Now you know what you're going to do. So I'll give you a couple of minutes break. Go and enjoy that break. When you come back, I'm going to explain to you line by line what you need to read and what you need to learn and to program. And when you come back, we'll open the IDE and I will explain to you line by line. So I'll see you in a couple of minutes. So go and enjoy that break, and I'll see you shortly here in 2 minutes time. So see you then. Until then, I'll catch you in a few minutes. Hello and welcome back. I'm sure you enjoyed that break. I will go and open the IDE. I already did the typing of the program, but I'll walk you through line by line so you can understand as well. So I'm just opening STM32 Cube IDE on the background, and I'll explain to you the today we are learning the I2C initialization code, so I will explain each and every line, and I'll refer that to the data sheet. I'll explain why those values are there, so you will have a better understanding. And then by the demo session on the third day, I will show that in the logic analyzer through pulse view, and you will show you'll be seeing the interface of the accelerometer. It's still loading on the background. I'm just waiting to be connected, and then I will show you the program that that I have written from scratch. Okay. So the first step, you know that you need to go File, New. You need to open a STM32 project that you know. You have to click on this. And whenever you ask for the new project to be open, it will always take some time, and it has to link with the internal files to select the target board. At this stage, you also have to connect your target board to your computer, otherwise you'll get an error. So please do have your hardware ready to do this, otherwise you will face errors. So I have gone ahead and done all this, so I'm just taking you through in case if you have forgotten how to do it. So this is how you have to do. Once it allows us to choose the board selection, so you need to go here and then to board selector, you know which board you are using. So I'll type Nucleo F411RE and choose that board, RE, and then click next. And you got to set a name. Today we are on day 23, so I have already named as day 23, and then target project type should be started as empty and then finish, and this will bring out all these files. So since I already finished doing that, so it will generate and it will give all these files. So starting with the SRC, the source, you need to open the source and go to main.c. So that's our main.c program. Initially, as you remember, it comes with a few lines, so I need to delete that. And today we also going to use the STM32F4xx.h, the built-in internal header files. As if you remember on the LCD session, we went and did that path configuration and the symbol declaration. I will go through again with you. I already did, but you have to create a folder first in your desktop and name it whatever project you are working with. So in this case, we are working with I2C. So I already created a project, and then you need to create another folder called target. This is where all the ELF files will be sitting in, your .source codes and the ELF files. If you go to debug, you will see the .elf file. So this is why you need to set this target file. And also go back and copy the extracted file for using the STM32 header, built-in header, and it always comes in a zip format, so you need to extract and put it out here. So you need to do three things. You need to first go here, go to drivers, so you need to include the CMSIS driver. The device is ST because we are using ST32, so you need to use this STM32FXX. So you have to come here, include, and make sure that's the header file, STM32F411. So you go here, highlight this, copy. This is the first step. And right click on the project tree, go to properties, and go to C build. In this, go to settings, and then in the settings, go to MCU GCC compiler. In the compiler, you have to click on include paths. So I already did the two paths which I'm showing here. So you need to just press the add directory path and paste that link here. Paste that link and OK, and that will add. So likewise, you need to add the core M4 as well. So the first step is done. I'll leave this open. We go back to the folder here. I'll minimize this. Yeah, okay, folder. I'll go back to the main folder, because this time we need to get the other path of the core. So it will be inside driver, and under core, click on the core, then under include CM4. So you need this file as well. So you know that it lives in this. So copy this link and come here and do the same. You need to go to C++ build settings, and then go to MCU GCC compiler, click on include paths, and go here add paths, and then paste that link here, and then hit OK, and those two links will be added. So after that, you have to click apply and apply close. So that means both the paths are added. The next step is to add the symbol. After you've done that, you come here and include this statement, this line hash include. The header file should always be written in quotes, double quotes, stm32f4xx.h. So you have to include that, and simply select this, and then do a right click on this and click on open declaration. That will open the internal header file declaration. In the header file, browse or scroll all the way down and copy the STM32F411 symbol, which is this one. We already copied, that's why it's highlighting. So copy this symbol and then go back to your project tree, right click on the project name, go to properties, go to C++ build, go to settings, and then go to MCU GCC compiler. Then this time click on the preprocessor, and I already used and pasted here, that's why you can see STM32F11XE. So click on the add symbol value, and then you just paste it here, and then hit OK, and XE will be there. So this is all the three necessary steps you got to do, otherwise you'll get some build error. So it won't be able to use the internal files, internal header files. So after you've done that, just click on apply close, and that will finish the job. And then you don't need the header file because we already used, so you can simply close, and then you can go and right click and build the project just to check at that stage whether you got any errors or not. Okay, so we done the first bit of including the paths and defining the symbol for the STM32. The next step is you got to define the macros that you're going to use it in your initialization program. First, you need to enable the GPIO port B, because we're going to interface this to an accelerometer ADXL345. For that, we are using the I2C pins, SCL and SDI. For this, we are using GPIO port B. So to enable the GPIO port B, this is macros are nothing but it's like a substitute. So when you write inside the function, you can use this label instead of writing 1U left shift 1. You can just write that label name. So that's what macros is. Macros is it's like a substitute. In this is a small program, so you won't see much difference, but imagine you are writing about 500 lines of code or thousands lines of code. You can't go and simply type 200 times of this, for example. So that's where the macros really come in handy. So you need to define, and to write the define, this is the example, hash define. This is how you got to write. As you know, GPIO port B is the bit 1 in the data sheet. I will also open the data sheet, just one sec. I can show where that is. I'm just opening my Microsoft Edge, just one sec. So you need to enable bit 1 as 1. So that means enabling the bit GPIO port B. Then we're going to define that we're going to use the standard mode and the CCR, the clock control register value. The standard mode, you know, it's 100 kilohertz and the CCR value is 80. Then you need to define the maximum rise time when it is rising. So that will calculate and come as 17. Then you start off with writing the initialization function. You know how to declare a function. It has to be written with void I2C1 of init of void. Then this is the first initialization program you got to start. What I did is I opened this and then I copied all the steps from this I2C init. I copied all the 9 steps from here. I went to IDE and I pasted all the 9 steps. All the one in green that you can see, those are all the steps. You need to comment that so that you can use that for the next line. So I'll make a space so it can be easily be visible for you to see that. Okay, and okay, so once you get all of this in there, and this is pretty much the initialization program. So I'm just waiting for my browser to open. Just one sec. I'll minimize this. It's still loading on the background, but I'll go ahead and explain the program in the time being. So as you know, you got to first enable the clock access to port B. We are using port PB 8th pin and the 9th pin, that's bit 8 and bit 9. So first you need to enable that peripheral bus for that. So as you know, after this you can go and set your debug operation. As you know, right click and then go to debug as, and debug configuration, make sure you are linked to the ELF file, part 1 ELF file, and in the debugger, as you know, you need to enable the interface because we are interfacing with the built-in programmer in the STM32. That's what this step is. And you got to also enable the serial wire viewer and then apply and then debug. This will change to the debug mode, and then you can see the special function registers. So in the special function registers, the first step is you need to enable the access to port B. So that lives in the reset clock in here. So you need to enable AHB1ENR, and you need to enable this GPIO port B. So that's port A, and this bit here you need to enable that for GPIO 1. So that's this step. RCC HB1ENR, then GPIO enable. Then you need to enable the clock access to I2C1. Again, this is the I2C1 is connected on the 21 bit 21st place, so count to 21, and the 21 bit 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20. This bit you have to set as 1. So this is the one that's connected to the CRCN. This bit CRCN, it's connected to the I2C1. So that's what you're connecting, that making that clock enable. Then the next step is you need to set the PB8 and PB9 as an alternate function, and that you're going to set as for what mode you're going to use it. As you know, there is 4 different modes: input mode, output mode, alternate function mode, and analog mode. So in this case you're using it for output mode, so you got to set those 4 bits as 0 1 0 1 because we are using PB8 and PB9. So this is PB8 16 and 17, PB9 will be 18 and 19. I'll show you once the data sheet is open. Just give me a sec. I'll open in the other way. to see if I can. It's loading on the background, just why it's taking so long. Sheet opens and I'll refer to where they are. Okay, you need to enable that and set those bits as output mode. So that's what I written. You can't write simply as 0 here. To write the bit as 0, you need to AND that bit with the motor register, and then you got to negate that bit. So you got to do that for 16 and 17 as 0, 1, and likewise 18 and 19 as 0, 1. So these 4 bits as PB8 and PB9. Then set those to PB8 and PB9 as an open drain. So the output type of register, you got to set that bit PB8 and PB9 as output typer. And then you need to also set its internal pull-up, because we're using an open drain and you need an internal pull-up. So you have to set this as an output type, because you have to set that as 0, 1, 0, 1. So it's output drain. In this example, it's given as 1, 0, 1, 0. So to write 0, you got to AND and negate that. To write the bit as 1, you just simply OR that with the bit. And then set the alternate function for I2C. Once the data sheet opens, I'll show. As you can remember from the alternate function table, every port bit will be connected to, used as a multi-purpose pin. So that pin will be connected and used as an alternate function. In this case, it's connected to alternate function register 04, and the A for 04, you have to set the bits 0100 of PB8 and PB9. So you got to set bits 3 to 0, 0 and 00. So that means bit 2 as 1, bit 7 to 4, so 4, 5, 6. The second bit and the sixth bit should be 1. So this is, I'll write it here, set bit 2 as 1 and set bit 6 as 1. This is to connect to the alternate function to use the I2C1 register, I2C1. Yeah. Then after that, you need to enter to the reset mode. To do that, to let the microcontroller know that you're using as an I2C bit, I2C mode. So you have to use control register 1 and set the 15th bit as 1. Then to come out of that, you need to just AND and negate, and that will come out of the reset state. So after the reset mode, the next step is to set the peripheral clock and set the standard mode and the CCR value. So those are the next steps. To set the peripheral clock, you need to use the control register 2, and the 4th bit you need to set that in the peripheral clock. And then the next one, you need to set the standard mode, that is you are using the I2C 1 for 100 kilohertz, and then the CCR value from the presentation you learned that and calculated it as 80. I'll save this because I made a couple of changes. And then you need to use the CCR, the clock control register, and you're going to tell what frequency you're going to set that. So that's the standard mode. Then you need to set the rise, configure the rise mode. So use the T rise register, and this is the label that we defined here. So we're going to use that, and that's linked. And then set the peripheral enable as 1. So this is the ST mode, rise time as 17. So we include it here. And then set the peripheral enable I2C 1, and you're setting the P as 0, because you got to do all of this when the peripheral enable is 0. And then call this function inside the main function I2C1 and init. Then you finish the program, go here, right click and build a project, this time just to check for any errors or anything else that you may have to do. So it is building 19%. Once it finishes 100%, then we would be able to see the compilation. So we got to patiently wait. It's going through. Still on 19%. It's still registering. I made sure I connected the board. Yes, it's connected. But sometimes it has to check all the internal files, so that's why it takes long time before it does all the process files. Like it has to change to, as you know, object file, and then it has to generate the .elf file, which is just did. And it's almost finished. Yeah, 98%. And this is a lovely sign, 0 errors and 0 warnings, so which is really great. And this is all for this session. So now you know how to write the program for I2C initialization. And with this I conclude here and go back to our presentation. So these are all the steps we learned to do today, and I showed you as in how it has all done before. My data sheet is not opening, so I'll show you. Okay, this is what we learned. We learned about what is the I2C and what are all the different registers that we're going to use in the different message format, that sending the address frame and the data frame and the acknowledgement bit and the read and write bit. In the next session you will be learning more function to link those address frame and data frames. And then there is another dedicated session where you will interface with the ADXL 345 and you will see the demo in the Pulse view logic analyzer. As I said, you have to also shape up your mind as well when you develop your skill. So please remember TFAR rules. TFAR is nothing but the T stands for your thoughts. So you need to have the more positive thoughts, the more anything can do attitude in it, and the thoughts will change to your feelings. And whatever positive feelings you will have that positive energy in you, and those positive feelings will turn to positive action takings. So A stands for action. So all these three, the actions will take you to have the results that you are after. That means your positive results. So always stay positive and think positive, and immediately your brain will be thinking only the positive vibes and positive modes. And to be really successful, put far. So that's what for positive transform that, and then through the feelings, through the actions, you get the end result. So PT far, you have to remember that. And please do remember to do your mindset involvement. So write your top 10 goals and write top 10 ideas to achieve those goals. Please spend at least 30 minutes to do this exercise, and also please spend another 15 minutes to meditate or pray, and use 10 minutes to actually visualize for achieving that goals, and 10 minutes to work out your daily plan activities, and 2 hours will get for your learning, get 2 points. Please do post all your achievements in this group, and this will really help each other to lift each other up, and we will also be able to learn from each other. Not only that, there is combo internships coming your way. I don't want to include everything under one course, so I divided into 3 different courses. We are in the advanced. Please do purchase all the 3, so you will get the whole Cortex M4 series. And then also these are all the courses that's coming your way. You will be the first person to know once they are ready, so that you can also update your skills on this area. I take this opportunity to thank you, each and every one of you, to go through with me, and for all your patience to learn about the I2C initialization. This is Arul Anbukarasu. I am signing off on behalf of A2DG. Huru for now. I'll catch you in the next session. Until then, take care. Bye for now.